will share my screen. Let's get rid of this view. Speaker. So I'm going to start here. Okay, so I put into the chat already the link to this page. So this is our homepage for the bioinformatics core, the team. This is what I run. And it's here at rockefelleruniversity.github.io. You will find information about us, but really this is our home for all our, I'm going to hide me so I'm not in the video, for all our training. And I think we're going to cover all of this during this course. So we have quite an extensive course we're going to get through. Let me just refresh this page quickly. Great. So first thing I wanted to come to on this page is our introduction to the course, just to give us a quick understanding of what we're going to be covering. So, you know, who we are, who's running this course for you, what are we going to cover, and how can you ask for help? So first off, we're the Bioinformatics Resource Center. So I'm the director of the center, and we have the team here, and it's Matt Paul, who's really running much of the training in our team now, and you're going to see him in the participants. And if you have questions, please feel free to ask any questions as you go along. Is this the link? Brilliant, thanks, Matt. And as I'm going to show you how you can get help, you'll also interact with Matt there. But Jidong Lu's in the team, Douglas Barrows, he joined us from the Alice Lab recently, Wei Wang joined us from the Green Guard Lab, and everyone here really involved in parts of this training. We also have some outside collaborators, including Levi, and Cooney locally, and some from our previous lives in the UK. And one thing, hopefully, which will come out as we go through this course, people tend to, as they come to the course, they often join us as collaborators for future courses. So they help us write the material, but also really they help join us in these sessions to support and help you guys, the next generation of people learning R, really get going and apply it to their own data. So we had some great people like Alicia, Greg, who just finished his PhD, and Rob, who's also just finished actually. All three of them just finished up. So what are we going to cover today? Well, in the course, we're really going to cover right from the very beginning. We're going to introduce R, which is the programming language of choice for us at the moment. We're going to introduce the NGS data types, so the different types of data you may handle from next generation sequencing. What does it really look like if you just opened it up in a file? We're going to then talk about how you can handle these types using R. And then we have some very tailored courses for how you analyze ChIP-seq, ATAC-seq, RNA-seq, and of course, I haven't written it here, but single-cell RNA-seq. On top of this, we have lots of information, and we have some separate courses on how we visualize this data. I think, you know, the visualizations we're going to show you are certainly publication quality. And all this, you know, has taken us many years to put together. And I think especially in the last year with Matt, we really turned this into something much more easier for us to manage, but hopefully a little bit more useful for you with the YouTube channels, with the help pages we offer. So we hope to introduce the concepts of processing and analysis of high throughput sequencing data. And you're really going to gain experience going from raw data in R all the way through to the end, publication level quality plots. We hope we're going to provide some reference material, so these courses stay online. If you come back, and often you won't have your own data maybe right now in this point in your career, but you know, in a year or so you gather your own data, you want to come back to the courses, these will always be up, they're always publicly available. We are going to maintain our YouTube channel. The only thing is we do update these courses regularly. We try and add material, so it may change, but being on GitHub the way we've done this, you can always see the old material. We actually, to say, we actually use this, what we're going to show you, we use this day to day in our analysis. So this isn't just examples of how you may do it. This is really how we actually do it in the lab. And if you do work with us, we can provide, let us know that you're coming to our courses, and we can provide some intermediate objects which will help you put some of this courses in context. And especially if you're analyzing your own data with us, we'll give you some intermediate objects so that you can pick this up at maybe not the early steps, but later on in the analysis. So one thing which was really fantastic me and Matt did over this lockdown period is we went and we turned all our courses into this self-compiling page, and you'll find our material. I'm going to step into it in a few minutes. But every course should look like this, and this contains enough information really for you to go learn, run this course from the comfort of your, obviously we're all at home or on our laptops now, but without necessarily being in the course itself. We've added, what's really cool is we've added ways of automatically testing this so that when we update something, when we change something, which we may do, as I said, it should always evaluate whether the course is still working. So you're never going to come across a course on our pages which just doesn't work or doesn't make sense. It is tested automatically. A really nice feature as well is, and I'll show you this when we get there, if you're outside of class, and we do have some exercises, and clearly we're trying to fit in a lot of learning in an hour, maybe 2 hours I think we have. If you want to get help outside of class, something occurs to you, we have links here, and you can click there. You need to sign up to GitHub. We actually have a course on GitHub we're going to show. But there you can ask questions, and me and Matt are monitoring this board, and we will be able to get back to you with some answers to your questions. I'll show that in more detail. We hope at some point we will be able to, the way we've built these courses, we should be able to put this into one long document for you. And hopefully sometime during the running of this course, we may actually put this together. So rather than having separate pages, you will have one long book which encompasses all the material we'll have. That said, the course is fairly long. We're going to go on for many weeks. Settle in, relax, enjoy. If you have questions, feel free to reach out to us, not just in class, but also reach out to me or Matt at really any point as you work through the material. Okay, so that's the introduction, and we can get through to our first session, and this is Intro to R. Feel free, if you have any questions, I understand Zoom, it's maybe a little harder, but you can just throw things into the chat. I will try and keep an eye on it, but if Matt sees it as well, he can try and field the questions too. So this is our page, and this is what all our training will look like. Move this a little bit. So on this page, we have, first off, just testing that the course and all the things we're going to teach work on all our systems. They do. We're giving you an overview of the course, what we actually want to cover. And what's really useful is every course we tell you what you need to set it up in this course. And this is in the first few slides anyway. We're going to need to go here. We're going to want to download a version of R for whatever system we're on, Mac, Windows. If anyone's got Linux, we're going to use that. Also say you need to install RStudio. So we're going to teach you R, but we're going to do that using an IDE, integrated development environment called RStudio. It's just going to make our life easier. It gives you a nice desktop GUI in order to do our programming. And then if you need any packages, we list here how you should install them, and you can just copy and paste this into your R terminal, and it will install all the requirements you need to run through this material here or also at home. For all the material you can download from this link. I think we have a link somewhere else maybe as well, but no, maybe not. That's the link. So if you click that, it's going to download this particular slide set, and I will open up my desktop and show you, navigate you around that in a second. Also, we're going to embed all the training inside these pages. So you can, if you wanted to, you can stay on the page and go through like that. It might be a bit small. We have our slide here. So you can go through our slides here online. Again, we're not going to remove these. They will always be online. You can also, a lot of people, because you can't search, I think, these slides, which is a bit of a pain, you can't do Control F. We also give you a single page version here. So that's exactly the same material, but now you can do Control F and find the particular thing you're looking for. And then, all our material here. And again, if you want to get help, course help, you have the link here, but you can see it in the top right. And if I click that, it's going to take me through to where all the material is hosted by us on GitHub. And you can ask, what is it called, an issue? You could say, Don't understand. And you can ask your question. That's a terrible one. There's no description. But this will then alert me and Matt, and we will go and have a look at what your question is. What we will do, though, is we won't remove them necessarily, close them. If we feel they're useful to other people, we'll keep them open, we'll mark them as resolved. So you might find when you come to this help page, maybe you had the same problem this guy, error installing RStudio, or you had this question. It's already there, and we can already see what the solution was. If not, ask the question. Me or Matt will hop on and try and answer it for you. Okay, great. Also, link to Twitter. You can follow us on Twitter there. All the slides are also at the links at the top. Slides, single page. We have the code as well, so just the R code in the slides. And then finally, we'll come across them in the slides themselves, but we have exercises where we ask you to do things like, very simple in the beginning, create vectors. But as we move through the course, we will move into more and more complex exercises. I do recommend following the exercises because we tend to build up. So the first set of exercises are very easy, but the second set will use things you've learned in the first set of exercises, and so on for the entire extent of the course. So we can get started. Okay, so I think today is going to be a slow session. We're just going to get started. We have a break in the middle where I will give you some time to do some exercises. I will come back at the beginning of the second session. We will quickly run through those exercises, and then we have one more session, and then at the end there's more exercises. Feel free to leave if you want to go. I will run through the exercises at the start of I think it's around 4:30. Okay, so let's get going. So this is introduction to R, session 1. First thing we're going to do is cover how we set up, how we actually get R on our machine. If you get stuck here and lost, we can help you in this breakout to get this R, the end of the first session, to get R installed. We have me and Matt. If you want, you can also ask a chat. Maybe Matt can take you into a breakout room or help you. Maybe we don't have breakout rooms, but maybe Matt can help you in the chat and get things set up. So the setup. So as I said on the front page, all the links to the course you can get here, and you should be able to just click and it's going to download that link and take me to a new page. So all the material you'll need is in there. I'm just going to jump to the next slide, and we can see actually what was in that download. Share screen. So my Zoom somewhere here. Great. So I downloaded the intro to R, and then if we look in here, we can see in here I have lots of information. Actually, if I click this index, I have a copy in some way of the course itself. And then I can go in here. Sorry, here's the index. Then I get the copy of the course. So in that download, you get everything which we have on that page. And then we have presentations, the single page, the slides. So, don't be worried about this course. If you're worried this course page is going to disappear, obviously download it, keep it on your computer. And as we get further on, we have the exercises and we have the data required for some of the exercises inside this packet as well. Okay, so downloading this gives you both the courses, the data, the exercises, everything you need. Wait, how did I? Oh yeah, because that's the one I downloaded. Okay, so this really just takes you through where everything is inside that structure. One thing we'll do, and we haven't even installed R yet, so we're not quite there, but we're going to have to set our working directory to be inside our download we just had, and this will allow us to read files and do some of the exercises later on. We haven't installed R, so we'll get to that bit. So what is R? I'm going to share my screen differently again. So what is R? R isn't a language like C++ or C, which is really built for speed and for running big networks of systems. R is a scripting language, and it is a great environment for statistical computing. Okay? And actually, this is what we do mostly day to day in the bioinformatics course. We use R. I think everyone in my team uses R day to day. And it is incredibly useful for what we are going to cover here, which is next generation sequencing analysis, but also proteomics image analysis. You can do all of this really wrapped up inside R. R itself was developed by two people beginning with R, Robert Gentleman and Rossa Harker. Perhaps slightly more famous to us as Robert Gentleman, because he also span off and started the bioconductor, which is the biology subset of the R scripting language. Okay, so the two R's who started it. And R itself inherits much from a language called S, hence the gag of R, which was made from Bell Labs. S wasn't publicly, I think it's not open source, so you couldn't run it for free. So they've decided to make a free version in that of R. What is great for R is it's really suited to high-level data analysis, not necessarily very intense computational programs are written in R, but it's useful for analyzing gene expression, higher level data analysis. It's open source and cross-platform. If you're on Windows, Mac, Linux, you can install it anywhere. It has great graphics capabilities built in right out of the box. And if you don't like the graphics capabilities you get there, it has an incredible set of add-on packages. And it's really, these packages, what other people have written, allow us to extend the base functionality of R, and that's what really makes this such a fantastic program or scripting language to learn. With that, packages, with people writing packages, clearly there are developers behind it. And I'd say R is a fantastic community of developers, both if you are trying to learn how to develop packages and new statistical methods, they're going to help you. But it also means if you're using their tools, these people are very responsive. Your tool doesn't work on my data. They actually probably reply and say, try this, maybe I can adjust it for you. Something which is really, really great about R, and especially Bioconductor, is it has incredibly thorough documentation. So we'll see this in the first few slides, but it is built into the nature of R to have every function explained, to have detailed what they call vignettes, but these are computational protocols, how to use a package, how to do an analysis in R. These are all built into the way R works. So like I said, R comes with these excellent out-of-the-box statistical and plotting capabilities, and I think this is probably, I certainly came to R for the statistical and plotting capabilities. I needed R myself to be able to analyze microarrays and to be able to make nice publication-level quality plots. And previously to learning R, I learned Java, much more low-level programming languages, and time it took to do anything which I was doing in R was 10 times, 100 times greater. Like I said here, great community of packages. R provides thousands, tens of thousands of packages which extend the base functionality. I want to make a plot of a map. I don't need to learn how to do all of this in R. There's a cartography package which will do most of it for me. Maybe Leaflet does it interactively in HTML. I just need to know how to work with that tool set, that package. A particularly useful set of libraries, as I said, was from Robert Gentleman, who developed the Bioconductor project, and that is the second half of all our courses. It's all Bioconductor. There we have hundreds of packages now. I think it's around 2,000, 3,000 packages directly related to computational biology, and 90% of them related to high-throughput sequencing experiments. High-throughput sequencing experiments. Microarrays, now high-throughput sequencing experiments. They do cater for proteomics. They have lots of other things, but just majority of it is what we will be looking at, high-throughput sequencing. So R itself is freely available as well. So we have these two components we need. We have R and RStudio. So R, if I click here, hopefully it will take me to the site. R is freely available. We can, if we want to, get the source code for it, trail through it. What we really want to do is probably just download an executable, which will allow me to install this on my machine. I'm Mac, so I'll click R for Mac OS, and here I have a executable or downloadable thing, which will install R on my computer. If you already have R on your computer, for now, don't worry about updating this. Again, if you have Windows, you can go here and it's going to go, you know, this is what you want. Install R for the first time. So we're going to run, let the installer run, and this will probably take 5–10 minutes in the background. But this is going to download R itself. So give me a second. So if we just look at what R itself looks like, R isn't particularly pretty to look at. I've got to just opened it up in a terminal. Here we go. So here is, you know, I've opened a Mac terminal. And this is what R looks like. Maybe I'll make that a bit smaller. Okay, looks like this. What we really want is a GUI or some framework to hold R in for us. So what we're going to do, going back to our slides, we're going to download R, but then we're going to download this thing, RStudio. Okay, so if we go to our RStudio website, it takes a little longer to get there. RStudio is still free to download the one we want, but they do have options which are pro or commercial. So we're going to get this RStudio desktop, and you can just go download here. And again, it's going to give you options of what you should download. I'm on Mac, so I'll download that. Once that's downloaded, I can start that. It will find the R on my computer, and I will get RStudio ready to go. So I don't want to stop sharing. Okay, so I say this R and R already installed in your machines. Actually, we're not in a lab at the moment, so you're on your laptops. So you'll need to go and download R and download RStudio, get that installed. Again, if you have troubles with this, clearly it's essential to the course. Let us know in the chat or let us know in the break at the end of this first session, so around 1:30, and we can help you get it installed. We'll share screen and help you get it installed. Okay, so let's have a look at RStudio. You have 4 main panels. I'm just going to stay on the slide for a second. I'll open up RStudio. We have our scripting panel. This is the top left, and this is typically where you'll write your code you'll want to execute. We actually have R itself in here. So this is where R is hosted inside this IDE. And then we have some useful panes here. This is most useful because it can tell us what's in our directories. It's like a little directory browser here, but it also things like help. And then we have up here our environment, what we currently have created, what variables we have. But what's really useful about this is we also have our history. So if we've been typing along and we're not quite sure what we've done, we can go in and have a look. So let's have a look at this in RStudio now. So I've, let me make a new RStudio session maybe. RStudio session. Okay, so actually I'll share this. Sorry. So once I've opened up RStudio, I already have some projects loaded, but I'm going to create a project here. I'm going to go create new directory. I think and I'm going to do new project. And I'm just going to type in it. It's going to create a directory on my computer. I'm going to do it on my desktop. It's easiest to find and delete later on. And I'm going to do directory intro1, create project. Create new file, create my R script. Great. So here we have our 4 panels we were just seeing in the slides. Okay, we have here the script. So this is where we would type things to go along. And we can save this using our save windows up there. We have here the RStudio. So this is exactly the same. I'm going to be a pain and share my whole desktop for a second. So if we look, we can see actually that this and this are basically the same, right? It's both running R, except one is inside a terminal, and that's all I have. In this case, I get this nice console. I have it here, but I also have my script I'm writing here. And I have my files directory here, so I can navigate around my desktops, etc. Where was I? R intro 1. Okay, so this is my present working directory. And we talked about this at the very beginning of the course, setting the working directory. If we want to do that, we just do session, set working directory, and we can just choose the directory we want our R session to be sitting in. So I'm going to choose here, here, and this is just following the instructions on the first few slides. I'm in here. Great. And now I have my presentation there, my data, which I might need to use for the exercises there. And if I want to execute anything in R, I can type it here. And I can, if I wanted to, copy and paste it into my R session here and evaluate it. That's not a very sensible thing to do. Sorry. Or I can just select things here and press run. And it's going to pass it from this script down to this session here. So this is just the R framework we're going to work in. We can actually now go back and start looking at what we're going to be doing. So just first thing we'll start with is looking at the different types of data which we can come across. We're going to start with from very simple calculations. R is effectively a calculator at its most basic. Then we're going to look at what variables are, just for those who've never done programming before, what is a variable? And then we will step through, probably today, most of this, the different types of data we can have in R. We have vectors, lists, matrices, and data frames. So as its most basic, as I was saying, R is just a simple calculator. If I type into the console 3 plus 1, it will give me a result back 4. If I type 2 times 2, it will give me 4. If I write square root 25 minus 1, it's going to give me 4. So just to show you that how it works, if I type in here 3 plus 1, right, square root, whatever, 16. Okay, so it's here I can type my commands directly, or again, like I was saying, we can type them up here. And I can just tell it to run that line, and it will evaluate it in the R session. So this most basic, R is just a calculator, and I can evaluate things like this. You can see here our first example of a function. Okay, so here, like a graphical calculator, we have functions which we can apply to numbers or other variables. Okay, so a function will just apply a complex operation on its arguments. So this is the function square root. This is the argument 25. And then it's going to return the result either to the screen or to another variable. In R, every language has their own way of setting this up. Arguments are provided to a function within these parentheses, and that follows the function name. So in this case, we had square root, and then the argument, and the argument was 25. I wanted the square root of 25, and then that provides the number, the value of the argument, the square root of the argument. Other functions which we're going to come across regularly are things like min, sum, max. And in these cases, we won't need to provide multiple arguments. I want to find the min of multiple numbers. I'm going to give it my first argument, my second argument, my third argument, separated by commas. Okay. Function name, parentheses, all my arguments are going to go in between there. And then what is the meaning of argument in this context? I think I'm going through it, but let me know if it's still unclear. So here, anything which we want to provide to the square root, an argument would be what we want to provide to the function to operate on. So in this root, the argument is the number that we want to get the square root of. In this case, min, we want the minimum of the arguments that we're providing. So in this case here, we can get the minimum of these three numbers, just min, parentheses, the arguments. Sum, we give it the arguments separated by comma. Max, again, arguments separated by comma, and it will go give us the maximum of this number, the sum of this, and the min of this. R has many built-in functions out of the box. base, we didn't have to load anything new in order to run square root. It has lots there. I have a list here, but it's so incomplete, it's not even worth clicking on. In addition to the standard functions we will get in base R, we're going to have lots of libraries, and like I said, thousands of libraries to do with high throughput sequencing, and these will contain specialist tools, specialist functions that we will use for things like sequence alignment, read counting, and all sorts of things we need for high throughput sequencing analysis. So then, given that we're going to have lots of functions which we need to use, how do we learn how they work? And I think this may answer your question a little bit better. Nia, I think. Yeah, Nia. Is, how do we actually know what these arguments should be to our functions? Okay, so I'm going to close my chat again. What we can do, and this is a really nice feature of ours, we can always do question mark, and then we can give it the function we want to learn about. So in this case, I was running the square root function and giving it my argument 25. If I wanted to know more about this, I can just go into RStudio. Obviously, I can Google it too, but I can do square root. And I gave it a question mark before, and then it brings up inside this panel on the bottom right a set of help where it explains a little bit about what the function does. So here it's got two functions on the same page. They both share the same help page. But square root computes the principal graphical root of x. If we look at this little bit here, which is the arguments description, it tells you what the argument I should give to this function is. And here it's square root. I'm going to give it something called x, and x has to be a numeric or complex vector or array. Vector is the next data type we look at. Gives you some more details, and often these are quite detailed. Gives you a reference, which can be very useful. If you're using a function which is more complex, it's nice to have a reference you can associate to a paper. And what I really like about R is it gives you at the end of every help page, every time you do question mark, whatever, it has to have a working example. Part of writing R packages is you need working examples. So if I took this, I can copy and paste it, and it will go off and run something. Right? But we're guaranteed from R, from this example, that we will get something that runs. Okay? What I really wanted to know here was the argument. Again, I think this is your question here. And here I could see square root takes one argument, x, and that has to be a numeric vector or array. Again, if I want an example, I can actually go there and look. Okay. So that's a very simple example, square root. Okay. Functions like min and square root, the arguments to be provided are obvious. Square root was going to take a number. Min is going to take a series of numbers. And for things like min, it didn't matter the order. Right? If I give it 546 or 645, the minimum number is still the same. Right? There's no difference in the order I give it. Not all functions are like this, and it can get kind of complex, but this question mark thing is going to help us a lot. Okay, so we're going to come across a lot of functions, and if we ever get lost, we just do this question mark, the name of the function, and again, it's going to bring up a help. And here we're going to try the function dir. So this actually gives you the ability to look at what's in a particular directory, and it will list them back to us. So we can just run dir by default here. If I run dir, it lists what's in my present directory, and I'd set my working directory earlier on to be here. So you can see it's just listing all the files and directories. Okay. I haven't provided any arguments to dir to this, right? But it still listed what was in there, and it gave me an answer. Okay. And that's actually because, let's do question mark dir here. It's actually because if we look in the help for dir, we can see it has all its arguments listed here, path, pattern. This is a much more complex function, but it's also got something called defaults. So here we can see the path is set to be dot. That means the current working directory. It's not looking for any patterns. It's not recursive, and that means should it list recursively into the directories? Does it list every file in exercises directory, etc.? All these already have a value assigned to them. So by just typing in dir, I get the result as dictated by these defaults. If I want to, though, I can then look in my arguments and I can decide that I want to change my path. And the way to do that is I can just do path equals, and I can just set the path. Now I want to search, and I'm going to go back and search my desktop. It's going to give now a list vector of all the files which sit on my desktop. I can change other things of this, so now I'm going to change full names. I'll change that now to be true, but default, according to this, it's false. And you can see now it doesn't just list the names of files, it lists the whole path to. So it tells me this is in this directory on my computer. Okay. So really functions, and we're jumping into this in the first few slides, but functions can be complex. What's nice is that behind the scenes we can just do this question mark and it's going to tell me what I can actually use with this function. Okay. What can when I type dir, it gives me the names of my current project. I'm not sure I get that one, but we can come back to that one. Yeah, dir lets you know what's in the directory. Same here. Can you revisit the set working directory concept? Yeah. So when we are operating in R, it has this idea that we are in a certain working directory. If I want to know my current working directory, we can always just do git working directory. It's a function again. And it tells me I'm in users, Thomas Carroll, downloads, Rockefeller University, and R course. So that's the directory my R session believes it's in. And if I run dir, it's going to list files within this directory. If I want to change my working directory, there are lots of ways to do it in R. But in R, we can do set working directory, and I can list, I just give it a vector of where I want to go. And it's going to now set my working directory to the desktop. And if I do dir again, I will get a different set. Easier way to set working directory for me is in RStudio. I can just go set working directory. I can choose the directory, and I get the nice browser. And here I'm going to go into what I downloaded, select R course, and then make that my working directory. By default, when you open the Files panel, it's also going to try and display your working directory too. If you ever need to hop back there, you can do this and say File, go to working directory, and now this directory matches my current working directory in R. Okay. This is going to become more apparent when we get to the exercises. So I think we'll have some questions there, because you're going to need to set your working directory, and I think it's in the start of the exercise, in order to read from here. Okay, so let's move on to variables then. So the very basics in any programming really isn't that you're just writing out strings of numbers. You want to be able to store these numbers, these results from your operations, from your expressions, as a variable. Okay, and a variable is effectively, in most languages, it is a value which is now stored as a letter or a word. Okay. R, like graphical calculators, like every programming language, makes use of this. And in R, to assign a value to a variable, we use this special operator. I don't even know how to describe it, @ operator. So if I want to assign the value of 10 to X, I got my variable X on the left, I point to it, and I give us the variable, the value I want to assign to this. Okay. Now, this newly created variable holds that particular value. Okay. So we can just see that in action. It's very simple. I can do X, and I can just assign to it. Well, if I do X now, it's 1. because I had already assigned to it earlier on, but I can assign it here. Now this is 10. I can create any variable. It can be any word I want. And I can assign that 10. Now our variable also holds the value of 10. Okay. Another nice bonus here about working in RStudio is as I create these variables, we can see them popping up in my environment here. Okay, so that one I created earlier on. But our variable I just created, you can see it here. If I change it, if I assign a different value there, I can see everything happening inside this panel in RStudio. Nice thing is, like I just showed there, variables aren't set forever. You can update them. So in this case, we set X to be 10. When I opened R, it was already set to be 1, but then I can assign a new value to it, and then X will take on the new value. Okay, so we can overwrite these values that we've assigned to it. Once we have a value stored within a variable, this variable here, X, will act just like the value stored inside it. So in this case, I'm going to assign the value 20. And we're going to do X plus square root 25. So it's going to take 20, add the square root of this, which will be 5, and give me the value. Okay, so we can start to use, once we've assigned to these variables, we can use them in place of the actual values. We can then use them in combinations. So we can use X now, add this 5, and then assign that back to a new variable. And then that contains the result of adding X, whatever the value of X was, to the square root of 25. So we can use variables together to create new variables. Oh, cool. Okay, that's fine. So in R, the most basic type of data we have is something called a vector. And a vector is an ordered collection of values. So what we've already produced, this X and Y, this X anyway, we've just been looking at, this is already a vector, but it's a vector of length 1. Okay, we're just using a function here called length. Length, if I give it a vector, it tells me how many values are in that. So I have one value, and that value was 20. If I want to start to create variables which contain multiple values, such as this vector, multiple value vector, we can use our very simple function C, which stands for combine, and it's just going to combine the arguments into one vector. So here I'm going to give it values 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I pass them to this combine function, and then it's going to combine this in the order that we put it into this function. It's now going to create a length 10 variable vector containing these values. Okay, so anytime I want to just combine two vectors or series of vectors together, I can use this C function to produce my now array of values. Okay. One thing we might actually do quite a lot is want to produce stretches of values. We're going to use this for indexing later on. To produce stretches of values in R, you can just use this notation. And if I want to produce, say, 6 to 10, I say start at 6, colon 10. And this is the equivalent of me typing in, C, 6, 7, 8, 9, whatever. And now just gives me back a vector of length 5 going from 6 to 10. There are other useful functions to allow you to create stretches of numbers, and we're going to do this a lot in our exercises now coming up soon. And these include things like seek and rep, again, functions with their parentheses. So seek, we can see what it takes if we do our question mark thing here. So if we do question mark, we can bring up seek, and we can see it's kind of complex. But we have a from and a to argument, the starting and end values of the sequence, by argument, the number to increment by, And those are really the ones which are going to be most useful to us. I have examples here as well, if I really wanted to know how it works. Okay. So given that, here we're going to say from 1 to 5 by 2. So it starts at 1, it's going to work all the way up to 5, and then it's going to do it by 2, so we'll get 3 in the middle. Another really useful function is rep. And you can do question mark rep to see all the details. But here it takes a vector, and it takes a vector here created with C, 1, 5, and 10. And then it's just going to repeat rep this vector 3 times. And that gives us 1, 5, 10, 1, 5, 10, 1, 5, 10. So we can now use square brackets to identify positions in these multi-component vectors and these arrays of numbers. We can actually use square brackets to identify index values within these vectors. Okay. So these indices, these indexes, are what we can use then to extract a particular value from these longer vectors. So here I'm just going to create a vector of length 10 here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so I'm going to use this seek command. I'm going to say from 2, 220 by 2. And that gives me a vector Z containing these values. If I want to extract from this the first value from my array, and this is different from some other programming languages, but if I want to get the first value, I do Z square brackets and I give it 1. Right? And that's going to take out this first value and actually returns a vector of length 1 containing that value. If I want the 8th value, I just do Z8. Okay. 1, 2, 3, 4, 5, 6, 7, 8. Okay. We can then use these indexes in slightly more complex ways, so we can actually have two index values. So rather than just selecting the 1st or the 8th, here I'm going to provide a vector as my index. So I'm going to provide value 1, 6 to my Z within the square brackets. And then it's going to go into my vector Z and extract the 1st, 3, 4, 5, 6, and the 6th value, 2 and 12. Okay. So by using our vector and another vector inside these square brackets, we can start to subset in more complex ways. We can also extract everything but. So this was going to extract the 1st and the 6th value. This extracted the 1st, and then this extracted the 8th. If I want to get everything except a certain value, so I want to take my vector but remove the 5th position, I can just put a minus in front of my index, and then it's going to extract from me everything apart from that 5th position and return back a vector. We can also do or use these indexes to actually not just extract values, but tell the R session what values we want to operate on. Right, so here again, I have my 10 values. My 5th value at the moment is 10. If I want to update that 5th value, I just tell it Z. I give it the square brackets. I'm telling it the 5th value. And now I'm going to assign to it a new value. And here I'm going to assign to it 1,000. And that's going to give me the same vector apart from the 5th position where I've updated this now to be 1,000. We can then use, as we kind of saw here, we can use vectors to index other vectors. And this can become most useful when we start to use variables. Right? So we have a variable here, y, which contains the values 6, 7, 8, 9, 10. I can use that y value now variable to subset or provide an index of my z. So here it's going to provide the 6, 7, 8, 9th, 10th values of z, and it's going to assign to them a 0. Now, not just the 5th values changed, but all these values have been assigned to 0. So we can start to update our vectors, not just one at a time, but using arrays of other variables to select what we want to update. So just to remind us, square brackets then we use for indexes. When we want to subset a vector at the moment, we do a square bracket. and we tell it the position in that vector that we want to operate on or subset out. For functions, we always use these other brackets. We use parentheses. Okay, so we want the square root, and the arguments that we pass to it would be inside the parentheses. Let's have a look to see how long until we've got our first exercise. Okay. So I might be a little bit over on the first one, but I will be under on the second. So vectors in R can be used for arithmetic operations as seen with variables earlier on. So like I said, we could do 2 plus 3, or we could do 2 plus y, and y has a value associated to it. We can also apply arithmetic operations to entire vectors. Okay, and this can start to become very useful. Here I've got my x vector, and that contains values 1 to 10. If I want to, I could times x, the entire vector, by 2. I'm going to here assign that to a new variable. But now we can see pairwise across this, every single value got times by 2. Right? 10 became 20, 9 became 18. Everything got doubled. We can also, add two different vectors together. So here we've got x and y. And if I add x to y, it adds the first elements together, the second elements together, the third elements together, fourth elements together. And it works along pairwise, adding these two vectors together in a pairwise manner. In this case, this is kind of straightforward what it's going to do. Right? It's going to take two vectors of the same length and add them together. When we're applying our arithmetic operation between two vectors of unequal length, it's going to be a little different, and the shorter one will be recycled. So in this case, I have a long vector, 1 to 10. If I ask it then to add another vector to this, 1 and 2, it's going to use 1 and 2 and then recycle them in the addition. So just to show you what's really happening there, 1 plus 1, we got 2. 2 plus 2, we get 4. 3 plus 1 again, we get 4. 4 plus 2 again, we get 6. 5 plus 1, 6 plus 2, 7 plus 1, 8 plus 2. So it's recycling this as it moves along. It uses them for the first two, and then it uses them again and again. Again, that makes sense when our x is divisible by the number of values in this one we're dividing by or adding here. When we start to do things which isn't going to give us a sensible result, so maybe we have 3 here, 3 values, that's not going to go into 10, so it's going to be recycled unevenly. It's actually nicely going to give us a warning. Longer object is not a multiple of shorter object, but it still gave us a result. Okay, so it gave us a warning, and it tried to recycle this as best it could, moving it along. A question. Okay, Matt's dealing with it, but I'll come to that at the end as well. I'll come back to that. Okay, so far we've looked at numerical vectors or variables. Okay, so it's very simple. We're just using C, and we can join these together, or we can use our seek, our rep functions, and we can create these long arrays of numbers as a vector, numeric vector. We can also create character vectors. In fact, we can create really any type of data type vector. Okay, if we want to create a character vector, we have to get our characters, which we want to create. So here I'm going to create a character vector containing Ictem, Commonwealth, and Wolfson. These are 3 buildings in my old place. And we just need to provide these characters in quotes. So Ictem in quotes, Commonwealth in quote, Wolfson in quote. And then I can do a comma between them as I would separate numeric arguments here, give it again to the combine function. And now I get what is called a character vector, which I can operate on really just like I did a numeric vector. So if I want to look at what the second value was, I can do 2 in square brackets for y, and it extracts out the second value. A really useful thing about character vectors is they can be used to assign names to other vectors. So they can almost be used as a key, a lookup key, right? So here I'm just going to create a vector 1 to 3, and then I'm going to use this function names on my vector, and I'm going to give it this vector of names of character vectors, character values. And now my vector here looks a little different. It's not just 1, 2, 3. It's 1, 2, 3, but each value has a name associated to it. Okay? And I did that by just creating this vector here, 1 to 3. I assigned the names from this other variable y, and now I have our first named vector. Like I said, this is going to be useful because now maybe I have a really long vector. I don't necessarily know the positions of my bits of interest, my buildings here of interest, but I can use here now not just the position, but I can use the actual names, which I've assigned here, to start to extract positions. So I give it my vector, and rather than giving it numbers, I'm giving it the names of the values I want to extract. Here, Iksa, Iktem, and Wolfson, and it extracts out just those values and it misses out the Commonwealth. So that's something we'll do a lot. We assign names to a vector, tables later on, and then we use indexing like this just to extract out the values we're really interested in. If, for whatever reason, you're not aware what's in your vector, and if you're reading it in from other sources, you won't. When you go and try and index by a position which isn't there, so here we can see we have index names Commonwealth, Iktem, Wolfson. We don't have anything called strand. If I try and pull out a value for this, it's going to give me back our first special value, and that is NA. And I think that stands for not applicable. There's nothing it can do here. And NAs tend to be handled in special ways in R. So like R, like many languages, when a value is missing, in a variable is missing, the value is assigned to NA. Similarly, not available. Similarly, when a calculation can be performed or cannot be performed, R will do NaN. So when it's, something divided by an impossible number or a character, it's going to tell you this is not a number. NA values allow for R, so rather than giving you an error or giving you something else, NA is handled specially in R. So when we start to produce these, and we're going to learn later on, we're going to have some ways that we can extract them, remove them from our results when we have either a not available, something went wrong in the calculation, or we didn't have a value for it, or if something did go wrong in the calculation, we have ways of dealing with NaNs. So when we start to see these as we move along, these are kind of special values inside R. The unique function is a really useful function for working with character vectors because it gives you exactly what it says in the tin. Given a vector of characters here, and I have gene 1, 2, 3, 4, 5, and then 1, 3 again. If I apply the unique function to this, it extracts just unique values from this longer vector. Okay, so gene 1 occurred twice, gene 3 occurred twice, but it doesn't give them back twice. It gives us the unique values from that. So we've seen so far numeric vectors, and we're going to have now, I think we just got another 5 minutes before the break. We've seen now numeric vectors, and we've seen character vectors. A really useful class of vectors is logical vectors. And these are vectors made up of Boolean values, so true or false. Actually, behind the scenes, I think it's ones or zeros, 1 for true, 0 for false. But we can create these just like we did a numeric vector or a character vector. We just give it C, and then we give it either this true, all capital, true, false, and those are the Booleans for true or false, or there is an alternative way of writing it. We can just write T and F, which is the equivalent. True is the equivalent to T, false is the equivalent to F. I have the feeling generally as you move on writing your own R, you're very much encouraged to write out true, full spelling, rather than ever writing this. Okay, it's much easier to write this, but you do get told off by various packages and programs. And I think it's because true can't be defined in R, but you can actually assign a new value to T or F. So just recommend using true or false rather than T or F in these cases. Okay. But either way here, we got our true false vector, Z, and then we can then use this like most other vectors. What's really nice is that actually we can use logical vectors to specify what indexes we would like to keep from other vectors. Okay, so if we have one here which is length 10, if we then create a vector 1 to 10 and I give it Z, effectively every time it sees a true, it will keep the value, and every time it sees a false, it's going to omit the value. So here we have staggered true, false, true, false. So I'm keeping one every other value. So once we've generated this logical vector, true, false, it's actually very useful then to subset our longer vectors into just those ones which were of interest, true or false. A common task in R is to subset one vector by the values in another vector. So I just want to keep the values which were overlapped. This function, and we're going to see flavors of this function later in high throughput sequencing analysis. This function in operator allows us to evaluate whether or not values in A match any values in B. So if we do A in B, it's going to create a logical vector of the length A to telling you whether or not A existed in the list B. So let's see that in action. Here we have gene list, and I've got gene 1, 2, 3, 4, 5, 1, 3. I've got a second list, gene 5 and gene 3. So we have a gene 5 here, a gene 3 here, and a gene 3 here. I can create now my logical index by following what we set up here. This is my A. Okay, so I'm going to get a vector, logical vector, this length back. And I want to know for this gene list, this list of vector of genes, which one of these occurred in the second vector. And you can see it gives me back the logical index like we want, the same length as this, except it says false, 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 false. Gene 3 is in the other one, true, false, false, true, false, true. Okay. Now we can use that to subset our gene list, and now I have just the genes in this one which actually were in this second list. So logical operators and logical indexing is very powerful. Vectors can be evaluated to produce logical vectors. This is going to make our life very easy for subsetting. And some really nice common bad timing just. Equals, greater than, less than, or later less than or equals or greater. So here I can start to use some of these operators to start to extract logical indexes, and I'm going to use that to subset my index. So here I'm going to create x is 1 to 10. I haven't actually written that out, but you can imagine. And if I want to then produce a logical vector assessing which values of x were greater than 5, I just do x greater than 5, and I get here printed to the screen my logical vector, the same length as x, false, 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 false. This is the 6th value, so it's going to be 6, 7, 8, 9, 10. They're all greater than 5. And then I can combine these two together. I can produce my logical vector here, x is greater than 5, which is this. And I can use that to subset my x by giving it the square brackets and just putting the logical vector. So logical vectors can be used in combination in order to index vectors. So you can combine the two different logical vectors together and evaluate to get the result of this. So the really useful logical operators to combine are AND, right? So this is the AND symbol. So this requires that both the logical operators are true. We have a pipe symbol, which is an OR symbol, which requires that either of them are true. So A or B. And then we have a really useful exclamation mark, which reverses the logical operation. So if I have a logical vector and I put exclamation mark in front of me, in front of it, it's going to turn all the trues to falses and all the falses to trues. Okay, so let's see this in action. X is 1 to 10. Just give me the values where X is greater than 4. So mark them as true. But then I put this exclamation mark in front of it. It's going to reverse it. So it would have been true, 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 true. But now it's reversed it. So only the first ones are true because they're actually not greater than 4. I can then do the and. So here I have, give me those greater than 4 and X is less than 7. So it's only going to be the ones in the middle where it was greater than 4 and less than 7. And we can do this kind of useless example, but we could do X is greater than 4 or X is greater than 7. That's everything. So they all become true. I think we're one slide off the end. So it's with these combinations that you can start to do really complex subsetting and operating. So here we're going to do X is 1 to 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And here I'm just going to extract those like I showed you here, which were true. X was greater than 4 and X was less than 7. So then that's going to give me just 5 and 6. And here I can combine now and X is not less than 7. Right? So actually X has to be greater than 7. So it's 7, 8, 9, 10. So that's a little whirlwind tour of variables and introduction to vectors. To get us going, I have a very simple exercise here, which involves some of the stuff we've done. Find the number of files in the present working directory. This might change depending on what you've downloaded. List the files, but it starts with just creating a vector, a little bit of indexing, and then it gets a little bit more complex as we go along, into the fact that we have some type of bonus question at the end. I recommend you give it some time to work through that. But if you get stuck or if you're heading off to some other meeting, or we have all the solutions on the slides on the next page. So work through the exercises now until 2:30, and I'm going to start again then. But if you wanted to jump ahead, you can also just look at the answers. Okay. So I think we had one more question. So I will see everyone, if it's 1:30, it was 1:40 now, I'll see everyone again at 2:30 for the second session, and I'm going to run through the exercises at the beginning of that second session. So I'm just going to try and answer this question from Carolina Zapta. This inside. Be mindful of that. Oh, was it? Oh, fantastic. Great. Brilliant. That's brilliant. Okay. So if you guys want to take a break, I'm going to take a small break. Matt, hopefully, I'm not sure if Matt's got time to hang around, but I think gap. Drop your questions into chat if you have any. I will be keeping an eye. But yeah, do try and work through this first set of exercises, because I understand it's quick to work through what we just did, but this is going to explain it all to you a second time. Yes, thanks, Matt. If you're having issues setting up, I'll hang around now. That's okay. I'm going to stop my video. I'm going to pause the recording. Great. Share screen. Okay. So we've dealt a little bit with how we can look at one-dimensional numbers, one-dimensional arrays of numbers. So, 1 to 10, 1 to 100, 1 to 100, but stepwise of 2, or our logical vectors, or our character vectors. Okay, so these are the basis for every data object we're now going to look at, to be fair. Okay, vectors are the very basic building block of everything else. And one of the most important types of data in most programming languages, but also data analysis, is matrices. Right? So this is now a 2D array. So no longer just one set of values, it's one set of values by another set of values, your table. And in programs like Excel, we're very comfortable working with this. And I think there's something about tables which we're very comfortable working with generally. So you'll have a columns, and these could be samples. You'll have rows, and these could be genes. And then, in this sample, in this gene, this is the score. This is the score for a different sample. So we like tables, and clearly there are ways of dealing with this in R, as there are in every language. The most basic way of holding a table in R is something called a matrix. Okay, think 2D vector. Okay, so matrix can be created using the matrix function. And we just need to supply something to put into the matrix, and then n rows and n cols. And we're going to supply a vector to put into the matrix, so like a one-dimensional array. Okay, so in this case, we're going to give it 1 to 10, and we're going to tell it, give us 5 rows and 2 columns. And you can see it goes 1, 2, 3, 4, 5, and then it's reached the end of the rows, and then it goes by column. We could do something, just change that around. N row is 2, n col is 5. But again, it's going to work down the columns. It puts 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Creating a matrix is very simple, as long as we have a vector up front. So by default, we see it's going down. Actually, that tends not to be the way we want to fill these matrices from our vectors. Often we want to go left to right. And we can control that operation, how that works, by using this by row argument. So here we give a standard matrix, parentheses, we give it what we want to put into the matrix, and we tell it how we want to lay it out, 2 rows, 5 columns, and it goes automatically down the columns. Here we do exactly the same, but now we just set by row equals true, and it's going to work along the rows first, and then fill up each row at a time. To find the dimensions of a matrix for a vector, we had length. Okay, and that's good enough because we just have a start position 1 and it goes on until it ends. The matrices, obviously, we have 2 dimensions. So we can use the dim function to give us the rows and columns, the number of rows and the number of columns. Or we have directly n row. If we apply that to our matrix, it's going to give us the number of rows. If we do n col, it's going to give us the number of columns. Okay, so n col and n row are the equivalent of length now, but working along the columns or working along the rows. So a matrix can be created from multiple vectors. So these things like 1 to 5, these types of vectors, or you can actually stitch together other matrices. So we can use this extension of combine called cbind, right, column bind, to attach data to a matrix as columns. Okay, it sounds column bind. We're going to stick stuff into columns. So here we have 2 vectors, 1 to 5, and then another one, 11 to 15. And I can just do cbind like I would have done C to combine vectors, but now it's going to put X in the first column and then Y in the second column. And now we have our matrix object, which we can operate like other matrix objects. RBind is a row bind. So this is column bind. This is now row bind. If I want to add another row, in this case at the bottom, I can put Z after our matrix. And here it's going to row bind onto the bottom of our matrix, this Z. And that was just 21 and 22. Notice is actually attached here because we've got a vector called X and we've got a vector called Y. When we cbind them, you can see actually you've got a column name here as well. We'll talk about that in a second. Here we have a row name of Z. So just like when we try and do arithmetic in vectors, and we were trying to say have a vector of 10 and add to it a vector of 3, they're not compatible in their sizes. We're not able to fit them evenly in. So when we're creating a matrix using cbind or matrix for incompatible vectors, it's the shorter vector is actually recycled. So in this case, here I'm going to do 1 to 5. I'm going to say, just give me 2 columns, but I want 3 rows. I haven't got enough data to fit that in. I've got too much space, right? I haven't got enough data to fill it. So what's going to happen is it's going to start 1, 2, 3, 4, 5, and then it's going to fill in from the beginning again. 1. Because it's not even, right? It's not beginning to fill in 1, 2, 3, 4, 5 again. It's going to give you a warning, and it's going to tell you, you know, this is a problem. Data length is not a sub-multiple or multiple of the number of rows. Okay, so you see that, you know, then perhaps your matrix hasn't been constructed properly. Similar for R-bind, like with vectors or here, except in this case, it's the longer vector, which is going to be clipped. So if I have a matrix with only 2 columns, and I'm trying to row bind a vector of length 5, it's just not going to work. It's not going to be able to fit it in. Right? So it's actually just going to attach. So we've only got 2 columns here. If I try and attach a vector of length 5, it just takes the first 2 values and it clips off the rest of it. Okay, so only those first 2. So these are important things to be aware of, because you're maybe not get the matrix you expected. Okay, but it will give you a warning. When you type this in to R, it's going to tell you off. Does it? Let's have a look. Exactly that, right? Data length is not a submultiple. Okay, it allows me to make it. So I do get the result, but it's told me the warning nice and clearly. So hopefully we will be aware of when this happens. Great. Okay. So as we've seen with vectors, matrices can be named as well. So we saw we could use the names function, apply that to a vector, and then we could use those names as indices. And this is really useful for long vectors. For matrices, we're going to have to use something slightly different, but we have a very similar concept of names. But because we have rows and columns, we're going to use col names and row names to assign, you know, the row names or the column names respectively. So we create matrix 1 to 10, 5 columns, 2 rows. Here we go. And now if I want to assign the names, column names to it, rather than put names, I do col names, give it a matrix. And here I'm using a new function, paste. And I'm pasting column onto the numbers 1 to 5, and I'm going to create them separated by underscore. So that gives me this column 1, 2, 3, 4, 5. And then I'll do the same for the rows, except I'm just going to have 2. And it's going to paste row with a separator of underscore onto 1 and 2, and then that's my row names. So we can, similar that we can use this to set our column names and row names, we can also use them to extract column names and row names. So here, col names on our named matrix brings me back those column names. Row names on that named matrix gives me back the row names. Okay, so these names I can extract and set using the row names argument. Column names I can extract and set using the col names argument. So now we have our table. We want to be able to start extracting subsets of the table, maybe rows or columns of interest to us, but also replace elements of the table, just like we have with a vector. Okay, so we can use a lot of the same tricks we've just learned with the vectors, except with indexing matrices, because it's no longer one-dimensional, it's two-dimensional. We have rows and columns. We can then provide 2 values to specify, you know, where in our matrix exactly do we want to extract or replace. Okay, so we're still going to use our square brackets. Like here, we have our matrix, we have our square bracket, we have the other square bracket the other side there, and then we have 2 indexes instead of 1. We have the row index, which goes first, and then comma, and then the column index. So we can see this in action here. This is our narrow matrix, 1 to 5, 6 to 10. If I want to get the first column, second row, rows are first, so it's 2, is that right? Rows are first, so we go 2, and then columns second, we go 1, 2, 1, it's going to give out that value, and there we go. Nice thing about this is we can actually extract whole rows and whole columns at a time. If I want to extract a whole column in this case, I can take our narrow matrix and I just don't put anything in the index position before the comma. So here I have 2, 1, saying get the second row, first column. If I just entirely leave out this index for the first, it's going to give me back the whole of that column, and it gives me back as a vector. If I want to get just the third row, I leave the column index empty, and now I get back I just specify the row index and I get back the third row. Yeah, you can also start to use things like multiple rows here. So if I want to get 2 rows back, I can specify here second and third as a vector. And of course, it has to return back to me a matrix. So I can subset my matrix, and I could do combinations of rows and columns to get particular submatrices from my major matrix. Okay, so all the indexing tricks we've learned before still apply, except now we have 2 dimensions to index by, rows and then columns. As with vectors, because the same tricks apply, we can use our column names and our row names to extract particular cells from our matrix. I'm just going to have to assign some column names first. So here I just assign 1 or 2 to our columns and rows 1 to 5. I guess it's 2. Yeah, it's 2 columns, 5 rows. And then if I wanted to extract the column named column 1, I can just do our comma, and then it's after this. I do, like I with vectors, I give it the name of the column, and it brings me back a named vector here with the row names now, the names of the values. And I could do it for rows as well. I can bring out the first row, and then it names the values by the column they were from. And I can use these just like I would numbers to pull out particular values from that table. Okay, row 1, column 1. As with vectors, matrices can be subset by logical vectors. So here we have narrow matrix. This is already named by columns. We have names by rows. I can pull out, as I showed you just now, the first column here, 1, 2, 3, 4, 5. And then I can apply to this, like I would a standard vector, our numeric operations, our arithmetic operations. So here I just want to take those in the first column and test whether or not they were less than 5. And it's telling me 1, 2, 3, 4. The last value wasn't less than 5. That wasn't less than 5. So we can then use those logical vectors this is creating, this true, false, true, just as we did with vectors now, to subset our matrix. Okay, so I can put this value here, this expression here. It's going to create the logical vector internally here, where the last value is false. And that means it's going to miss out this last position, the last row, when I do the indexing by row. So here I've got my comma, I'm subsetting my row, I'm indexing my rows, and I'm saying just give me those where the value of the first column was less than 5. As with vectors and matrices can have arithmetic operations applied to the cells, rows, columns, or the whole matrix. And I'm not talking about matrix operations here. I'm just talking about we can apply a number, we could times the whole matrix by a value, we can log the whole matrix in one go. So here, if I wanted to just add 2 to my first row column, I can just do +2. If I wanted to add it to every value of my first row, I can take out the row and then do +2. And this takes out this and adds 2 to that, 2 to that, 3, 8. What's nice is we can also apply, I guess this is it, we can apply arithmetic operations to the whole matrix. And in this case, the function mean takes a matrix and it's going to go and find the mean of the whole matrix. I don't need to take a mean of every column or every row and then take a mean of that. As with vectors, where we want to replace portions or the whole vector or a particular index with a value, we can do that now with matrices. We have our narrow matrix unaltered here. If I want to replace the first row, first column, rows before the comma, columns after, and then can assign 10. Now I have 10 in my position. If I want to replace the whole of the second column, I can do (2), and that's the whole second column because I have no row index, and I can now assign that to be 1. And then I can edit my matrix and update it in place. Okay, getting close to the end of this particular session. a really important feature of a matrix, and we're going to touch onto this, I think, next time now. We might cover factors today, but covering this probably next time now. A really important feature about matrices is they have to be one data type. Okay, and it's actually the same with vectors too. They can either be all numeric or they can be all character, but they can't be partially numeric and partially character. You can't have a logical in one part of your matrix and the rest of it's all numeric. Okay, so here we have a narrow matrix. I can times that by 2. Okay, and I have my values back here. But if I try and put in, this is our matrix at this point, and it's all numeric. If I try and replace one value, just the first position, first column, with a character string, it's going to turn the whole matrix into characters. Okay, so now I think I can't apply arithmetic operations to it. So notice I'm not even affecting column 2 directly. Right? I'm replacing something within column 1, row 1. I'm replacing that with something which, yeah, makes sense. I can't times that by 2. But as soon as I've done that anywhere in my matrix, the whole matrix nature's changed. It all becomes character. Okay, and then I can't start to do these operations. So we need a different data type to allow us to mix and match numeric in one column, maybe logical in another column, character in another column. We want something different, which is allowing us to handle that. Matrices are great because often you do have a matrix and you expect it to be all one type. And the example we keep saying is something like expression measures. You will have an expression measure per sample, per row, and they're all going to be numeric. Matrix is great for that, and we can apply all these easy operations on them. But when we start to have things like metadata, where we have mixtures of numbers, maybe patient weight, height, and then name, and then some details about them, we're going to have mixed nature of character strings, numeric, and matrix just won't hold them. Okay. We're going to have issues like this. So we can come back to these exercises, and I'm going to skip forward just into the next type of data, and that is a factor. And I don't think these are too much before we would jump into data frames, and we'll do that next week. So a special case of a vector is a factor. And factors are actually used to store data, which we can then group into categories, categorical data. Specifying data as categorical data in R allows it to handle the data, I say properly, but it really gives you access to special functions you can apply to factors. And I think we have a nice example here, just even maybe in the next slide, where you can do things like summary, and you do this to a factor, it will give you a much more sensible result because it's expecting the data to be categorical. We can make our vectors we already have into categorical vectors, factors, just by using this factor function. So I'm going to create a vector here. It's going to be male, female, female, female. Right? I'm going to create that, and that will create a vector. If I want to turn that into a factor, I just give my vector to the factor function, these parentheses, and it returns back to me a factor, which looks very much like our vector, except has a new component, which is levels. Okay. If I want to extract the levels which are attached to my factor directly, I can actually call the levels function on my factor, and it tells me I have 2 levels. And you can think of these as the categories available in my data, female and male. So you can already imagine that this is going to be useful because I don't actually need to go and do unique or interrogate my vector to find out what are the different categories I have. They're already here. But also by placing things like this, it's going to save space internally by creating this object. So it actually helps R a little bit internally too. Yeah, this is the exact example I was showing. So a nice feature of summary, a nice feature of factors and the special nature compared to vectors is something like the summary function. So in this slide here, I created a nice vector, male, female, 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 and then I turned that into a factor. So it contains the same information. If I do summary of that vector, it just gives me some useful information still, this summary function. It tells me the length, It tells me the class is character, and it tells me the mode is character. So it's telling me really some useful information. If I do summary on my factor example, though, my factor version of this, it's starting to give me some statistics almost. It's telling me I've got 3 females and 1 male. That's what I would like to get from my categorical data. In our factor example there, we saw that the levels were displayed, and this is going to affect you in plotting later on and some other things. We saw that the levels can be displayed in an alphabetical, sorry, chat. Oh, yes. So I think I just explained that. There is, so unique is for vectors, right? So you could extract very similar information. If I got unique on a vector, or if I applied levels on a factor, right, it's going to give me the unique values within that factor or vector. There is a difference though. So if I call unique on a vector, I believe it gives you the unique order as it occurs in the file, in the vector. So I call unique, and it's going to give me the unique values, but it's going to put them in the order that they were discovered in the vector. For levels with a factor, as we're showing right here, actually it's really important. So the order it comes back. And that's because later on, factors are used throughout R. When we start to do things like plots, when we start to do things like DSeq2, differential analysis, it's the levels which decide the order in the plot or the order in the statistical testing. So in this case, the fact that female became before male, when we get to plotting, R is going to look and say, okay, the levels, female is first, male, I will put female on the left in the plot. Okay, whereas I think if we just do unique, and we can test this is true, I think it's just when it comes across a value, it just puts that in that order. Right. Here, female's first. I think if we did unique, male would come up first. Let's test that. It's a good question. There you go. So that's true. So a factor is a different nature. Like I'm saying, it's categorical. It's handled differently. But it likes to order the levels alphabetically by default. So here we have female first and male. Whereas when we did the unique, it just came across male first and then female later. Okay. So summary. So yeah, so then we're saying levels are important, but how do you control that, right? We didn't do anything here to make it so that female was first, male was second. Right, it's done it alphabetically, but we can control it, and we can control it by when we set up the level, the factor, we can actually supply an additional argument, levels, and we tell it, I want male to be first and I want female to be second. And now when I get the factor, you can see male goes first, female second. And actually, when I do the summary, I get male first and female second there. Because earlier on when I did summary, female came first, male came second. Okay. So the levels are really important in factor in deriving order for plots, things like summary, how other functions want to present the results from them. But we can control this ourselves when we create the factor. I'm not going to show you, but you can actually use levels argument as well to alter a factor's levels. Okay, but this is often the neatest way of doing it. Maybe I am going to show you that. Okay. Okay. So one real pain about, oh wait, order of levels. Okay. So in some cases, there's no natural order of the categories. Okay. So this example, male and female, one is not greater than the other. Okay. In other cases, you actually do have some need to have categories small, big, biggest, and you want to be able to convey that in a factor. So here we have just normal ordinal data, ordinal data, categorical data. We have factor, and we give it our vector, and we tell it the levels. But if I try and do something like factor 1 is less than this, it's going to tell me, look, this isn't meaningful comparison to make for a factor, and it actually gives me back this result we discussed, this NA, right? Not available, not applicable. Sometimes we do want to be able to set these things are greater than others. Like I said, small, big, biggest, we may want that, and that would be our ordinal data, ordinal categories. So we can specify the categories to be ordered. When we build our factor, we give it the data we want to put in, we tell it the levels, right? And we tell it it's ordered, and that's true. Okay, so by default, this is false, but it's here, the order of levels in here now is meaningful, right? So it's now going to be reflective. So when we do something like factor example 1 is less than factor example 2, it knows to interpret it as ordered and less than. Actually, when we just type in factor example now, rather than just seeing the levels side by side, it actually also gives us this less than, right? So if we had multiple, you would have another one less than, less than. So it can be useful to have ordinal ordered factors as well. Factors which aren't just categorical, but have an order to the categories. The real pain with factors, which I think is one of the biggest annoyances in our, and we will solve in our sessions 1, but this is going to keep on popping up, is like, unlike vectors, and because they have this concept of levels, you can't just replace a value in a factor, right? Because it's not going to be within the levels for that particular factor. So in this case, I just want to replace, I got my factor small, big, big, small. If I want to change this first value to big, that's okay, right? I'm going to get my factor example. Now it's big, 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 small. And that's because big is actually in the original levels. When I created the factor, I had small and big, and it got put into the levels of the factor. Now, if I have the same factor, which doesn't, we can see the levels here, it doesn't have one called huge. If I try and change this first value now to huge, it's going to say exactly what we were just saying. It's an invalid factor level. This level doesn't exist. And it's going to generate an NA. Now I have an NA value in my first index in my vector. Okay. So this is easy to solve. All you need to do, add a new level to your factor. You can do that using levels. Give it your factor, and here we're just going to say big, small, and I will add in huge. And now, once I've added it to the levels, I can start to add this into my factor. It's aware of what huge is, right? So I can actually put it back into my factor. Okay, so that's going to be the end of the session, I think, for today. We have another session on Monday, and there we're going to hop into this data frames, which is what I was mentioning about matrices. You can only have one data type. It is data frames which allow us to have multiple data types within one table, so that we can start to use our indexing and subsetting, but still run numeric operations on things which are numeric. So we have one exercise now, which I think I want to give us some time to do, and it was back here in the matrices. And this is a little bit more complex. So if you want to run through this, I will be back here at 4:30 to run through these exercises. If you don't worry. I am going to try and record this next session of exercises. And I'm going to go back and record the first session for our partners in China who are joining us soon. Okay, so I'll see you all at, if you have any questions, I'll be around for the next 10 minutes. If anyone wants to come back and work through these, run through of the exercises, I'll do that at 4:30, but I'll also record that. Me and Matt will try and put that on our YouTube channel later. Cool. I'm going to stop the share temporarily. I have a question. Great. So where were we? Share screen. Let's do the desktop. And we have the exercises on the right, and then the solutions and R open on the left. Maybe I'll actually open the solutions, make my life easier for myself. Recording, yep. Okay. So we are at matrices. These are the 2D arrays for one data type, and that's the important thing. Matrix can only ever hold numeric, character, logical, but it can't hold a mix. And it's going to default to character once we start to add any character vectors anywhere in this matrix. So what do we have to do here? Create a matrix containing information on gene names, okay, expression values, and gene lengths. So I think right out of the box, we have that problem. How are we going to put any characters in here? Right, we need to add gene names. Gene 1, gene 2, gene 3, but we have expression values. Actually, we're going to do a trick, and we're going to use the row names to hold this character information. Okay, because there's no limit on putting characters in the row names here. It's not going to affect the rest of the matrix. So to build this matrix, I'm just going to take these three here, give us our 3 vectors we need. So let me clear that down a bit. So we have the gene names. We have the expression, and we have gene lengths. So we can make a matrix by C binding, column binding these together. So we'll take our expression. I can't remember the order I do it in. That looks good. Gene lengths. Okay, so if I just C bind these 2 vectors here, expression and gene lengths, it's going to give me already quite a nice little matrix where I have 2 columns, and I have expression as the name of my expression column, and gene lengths as the name of my gene lengths column. So it's taken the name of the vector here and built us a matrix with all numeric, and it's named the columns for us, which is great. So actually, I want to assign that to something. So we have gene matrix, and then we can look at that now. Okay, so now we have gene matrix. We want to add row names, and they're going to be the gene names. So I can see row names by looking at a matrix with row names, parentheses, matrix, as it's null. And this means nothing's there at all. We don't have any row names, and you can see they're empty. So here we're going to now give it some row names, and I'll give it the gene names. Now if I look at our matrix again, it's got something I can index by, and also I've got row names. Cool. Update the matrix to contain the expression over the length, so this normalized length as a final column. We actually did that in the last exercise. So how are we going to do this? We can get gene matrix. I can get the column I want, and I want to do expression over gene length by using an index, right? So we have names as the columns here, column names, expression. Okay, and then I can do the expression matrix, expression vector over our gene lengths. This here matches the name of the column, right, which was the original vector name. And then I've got my normalized gene lengths. I'm going to assign that to my LNE vector, and this is exactly what we did in the exercise last time. And now, if I want to add that to my matrix, I can just C bind them together. Right, one's a matrix, one's a vector, but this has the same number of elements as we have rows, so it's not going to be a problem. C bind, what do I call it? G matrix. Okay, so I should have a new column called LNE. Great. Okay, update the matrix to contain the, oh, I just did that. Create a smaller matrix containing genes that are longer than 200. So this is just subsetting. And to get anything here, I would need to first create or extract the values for lengths. So again, I can get gene lengths. We have gene lengths, and then I want to get those greater than 200. So I'll get my true false. It was the second one, which was greater than 200. Oh, and the fourth one, sorry. And now, because that's a logical vector, I can use that to subset, and I'm going to subset my rows. And I'm going to do gene matrix. So I'm taking the gene matrix and I'm subsetting to the rows where the column value is for gene lengths is greater than 200. Perfect. Okay, and I assign that to something else. Or I'm not doing anything else with it anyway, but we get the same result here. Oh, I've lost my gene lengths column. Oh, I need to extract the gene lengths column as well, is it? Okay, so then I can, perhaps I could just do one. I'll take the first column and the third column. Okay, I think maybe here, oh, I've used the names to subset. That's even better. Okay, so rather than putting numbers to index the columns I want, I can actually list. I want to take the expression column and the LNE, and I'll use their column names as the index. Perfect. Okay, bonus question. These are always fun. Calculate the sum of expression and length columns for only genes greater than the length of 100. Okay, so we've already got something close to that here. Just change that to 100, and that's going to just give me a matrix where genes have length greater than 100. I only lost one, this one here. Okay, so then it wants me to get some of the expression and length columns. So I want to get the expression column. I can just index, and that's going to give me the expression column. And to get the sum of it, I will take that vector and I will do sum. Okay, so sum just takes, I think we saw this before, numeric or complex or logical vector. So in this case, we're giving it a numeric vector. Do the same for gene lengths, and I will get that. I think the point here is actually kind of nice. Let's do that one just to get that result complete. Okay, so we could actually run the sum after we extract the relevant column information. We also have some functions available to us, and we haven't covered this, but col sums. Right, so we can put col sums, and we can apply this to a whole matrix. And if I give gene matrix at this point, it will give me the sum of every column. So that's pretty close to what we want. We just need to subset the gene matrix before we run this, so I can do that. Now it's just going to give me the column sums of the gene matrix of just the genes with length greater than 100. And that should be good. Oh, I don't want LNE though, so I could do minus index here and get rid of the LNE column. Perfect. So that's the end of our session today. If you have any questions, or you want to run through something else, let me know. Issues are on the, you can find help by going back to our main page and going to get help. And then you can ask a question here if you get lost and you're not in class. Okay, so I'm going to stop the recording now, and I'm going to quickly run through the exercises I didn't record earlier on. Or maybe I'll just continue. I'm just going to continue and I'll stitch them together later. So going back to the exercises earlier on, we had the vector exercise. So, right. So remember vectors, these are these linear array of values. They all have to be the same value. They have to be numeric, logical character. I'm not sure if that was meant for me. Carolina. Sure. Great. Great. So let's do the vectors exercise. Create a vector containing the values 1, 2, 3, 4, 5. It's pretty simple. We can just type in C, combine, and give it the values 1, 2, 3, 4, 5. And we can just do that right here. So here, we can create any vector like this, really, can we? 1, 4, 5, any vector we want that way. Just combine them, and we have our values, and then we have the values or arguments we want to combine separated by commas. Okay, create a vector containing the values 1 to 100. In reality, this is just to stop us doing this. We're not going to type out C 1, 2, 3, 4, 5, 6 all the way to 100. So we can start to take advantage of some of these tricks in R. A really easy one is just to do x, and we do the lower limit of our range and the top limit of our range, and it gives us, you know, the interpolation, every value between the bottom and the start. If we want to get a little bit more complex with our ranges and have staggered steps in our ranges, we can actually use this next example where we have create a vector 0, 5, 10, 15, 20, effectively from 0 to 20 in steps of 5. So let's have a look. Okay, so seek, and we can go from, if I actually look up the help again, we did this earlier on, we can see the first argument to seek is from the beginning value to where we want to go to, and then by, if we read here, the number, the actual increments between each step. So here it's 0, 20, and our increment is 5. Okay. Create a vector containing the values 1, 1, 2, 2, 3, 3. This is just to show us that we can string together other vectors. So I'm going to copy this into my session here. But we can see here, the first thing we do is repeat the value 1 twice. And then we're going to repeat the value 2 twice. And then we can repeat the value 3 twice. And then we can just stitch that all together if we wanted to using combine. And it's going to join all these vectors together. Okay, so then we get 1, 1, 2, 2, 3, 3. There is a combination of rep, which will actually give you that in one go. We'll come to that at the end. So create a vector containing the values 1, 1, 5, 7, 8, 5, 7, 9, 10. This was again just to show you can mix and match all these. So here it's the same setup really. We have this 1, 1. We already had that last time, rep 1 underscore, sorry, rep 1 comma 2. So first argument, and then repeat it 2 times. And then we can run seek to give us the values between 5 and 9 with a step of 2. And then we just patch in 10 at the end. Create a vector of the values 1 to 10. I think this is just to get us going, so we know how to do that. Okay, so we can do just 1 to 10, give us the values 1 to 10. Create a vector with all, so let's skip to this one first, because this is a bit out of order. So if we wanted to create a vector with all but the second and fifth value, we can just do our negative indexing. So we have x, and we can go -5 will remove everything apart from the fifth value. It will show us everything apart from the fifth value. We want to remove the second and fifth. So we'll provide a vector. This would give us, back the second and fifth. And we want to do the reverse, everything but the second and fifth. We just put the negative, so we put minus there. This one before was a little bit more complex. I think this is a nice example though. So we have x, and we want to get the first and the last value from my vector. So we know the vector is 10 long, so we could do I have to get everything but the first and last. So we could just do, knowing it's 10 long, I can do the first is 1, the last will be 10, I do the negative. But if you don't know how long your vector is, say it's been passed to you by a different part of the program or script, the last index of a vector is always the same as the length. So we have x here, this is 10 long. So if I do length, I get 10, and I can always use that to extract the last vector, the last value in a vector. So in this case, we're going to do x, and we're going to get the first and the last, which will give us 110, and I think we do the reverse to get us everything but the first and the last. Next thing is square root. And again, this involves some indexing here, but really the trick is we have our subset to 6 and 7, right? I think a lot of people would try and do like a vector of the square roots like this, where you would extract the 6th position first, square root, and then square root. So you would do them separately, and then combine them together using RC function. I think a lot of people would do that naturally. That seems appropriate. But a nice thing about R, generally, I guess, programming languages, but in particular the square root function, So if we go look at the help, we can actually see the argument it accepts is 1, it's x. But this is a numeric or complex, vector or array. So it doesn't need to be one value. And in fact, when we went down here at the examples earlier on, which we ran, you can see it's giving it xx, which is multiple values. So we don't need to do this separately and stitch it back together. Square root's going to accept a vector of numeric values or complex values. And it's going to turn that square root every value in the vector. It's going to do its arithmetic operation along the vector. So I don't think we have too much left here. Create a new vector of alternating positions. Okay, so this is just, we can use seek. If we have x, and then we do seek 1 to 10, and we're going to do steps of 2, right? Then that gives us 1, 3, 5, 7, 9. And I can use those to index, and it's going to give me the first, third, fifth, seventh, ninth position out of x. Okay. So now we're going to get into the dir and some more work there. We think this is the first function we saw. Find the number of files in the present working directory. Well, this really depends on your directory you're in. So I'm going to go and just see where we are. Sorry, I'm going to try and pull that over. So if I look at my working directory, and I can go there like this, go to working directory. 1, 2, 3, 4, 5, 6, 7, 8 files or directories. If I do dir, shows me those 8, and then to get the total length, I can, this is just a vector, right? A name character vector, so I can apply the length function to it. Perfect. 8. We have 9, but I guess it was a different directory when I built this. And then if we want to get the first element here, I can assign x to the results of dir to a vector, a variable, and then we have our vector. And I can index that just like I would any other vector. I can pull out the values from it, or the last value in it. But I think in this case, I wanted the first. Okay, so the last questions, create a vector of the gene names. So we're going to do this. We kind of just covered this actually in the matrix exercise because we're going backwards. But let's do this first bit. We create 3 vectors, 1 all character, 2 all numeric. The last 2 are all numeric. Okay. All we want to do is assign some names to these numeric vectors so that we can index them by genes later on. I'm going to do that here by assigning names, gene names. So I do that. We can now look at these and we can see rather than having just 100, 300, 200, or 1,000, well, I guess I'm looking at a slightly different thing now. It's now got an index and name for every value. And I can use that if I wanted to extract the gene length for gene 1 by its name. Find the longest gene. So we're going to use here to find the longest, it's going to be max. So we can do gene lengths. The max is 3,000, but we need to know where that is. So I can use our logical match to do gene lengths in max. So it's telling me of all the values in gene lengths, which one matches the maximum gene length, and that's this one. And then I can, what am I meant to be doing here? Then I can identify genes, find the longest gene. Okay. So then I can get my subset, my gene lengths, which should be named. It's telling me gene 2, but if I wanted to pull out the actual gene 2 only, rather than the named vector, I could then extract that with names. Key. Identify genes which have a length greater than 100 and an expression greater than 1,000. So here we're going to take the gene names vector. We know it's the same order and length as these other vectors. And we're just going to do subset it so that we have gene lengths greater than, I think it was 1,000, 100. And in this case, we need to do and expression greater than 10,000. Okay, so that's going to tell us that. If we did or, it's going to give us very different answers. Okay, because it can be either the gene length is greater than 100 or the expression is greater than 1,000. But I think in this case, that one's the only one greater than 1,000 anyway. Okay, and this is the last thing we did actually in our other exercise, is calculate the expression over the gene length for all genes. And this is just to show us we can do this arithmetic operations where we can divide one vector by another vector. So if we have expression and we have gene lengths, I can divide one by the other, expression divided by gene lengths. And it does this pairwise division where this is divided by this, this is divided by this, this is divided by this, this is divided by this. Now we have our length normalized expression. And finally, we want to identify genes with length normalized expression greater than the average. Or we'll just take our vector and say greater than average here, I guess I mean mean. And that tells me the third one is greater than the mean. And then I can use that logical vector to index my original gene names vector. So there we have, or I could actually, probably more sensible to subset my own vector there. So let me, okay. Same answer, just different way of giving it. Okay, so that's the end of the session and the exercises for today. I'll see everyone, the one person who's left, next week. Cheers, bye. Hey, Matt.